Thanks very much, everybody. So I'm very sorry. It's not possible to make a quick trip to Paris for a couple of days to be there with you, but it's an extremely sad occasion. Somehow um, so I, well, I don't have so many good photos of Anatoly Moisеевич, but maybe this is one I really like. Uh, and what I like about it is that, he's always was he always had this point of view that if you have some combinatorial structure, real combinatorial probabilistic structure, and that can be of growing size, then you should always look at it from infinity. Somehow, if you look at it from infinity, then uh then this organizes your thinking in a way which is different than looking. So instead of looking at numbers 1, 2, 3, 4, 5, and so on, from so to speak, beginning, look at from the end. And this organizes your thinking in a different and very fruitful ways. This is why he was such a huge fan of limit shapes and this sort of phenomenon. He was it was clearly really dear to his heart. He uh he really he really somehow believed in that, and he converted many people in his uh I don't know. It's not faith, it's philosophy, right? Philosophy. And that certainly had a huge impact on my own work. And so, of course, in Russian, for those of you who don't know the language, there's a constant use of the expression, so to speak, you know, from the somehow, from the point of view of infinity and eternity, so вечности и бесконечности, and and that's just to somehow he would always speak in terms like that, so from, so to speak, infinity and eternity. And it would seem for many years that he was just so full of energy, somehow had more energy than anyone. Well, very few people have had his energy, and it would be, for many years it looked as if he would be going from the beginning of the natural numbers. But now he's at infinity. He's from there, from kind of the end of this street of umbrellas. Uh, well, I mean, I certainly this is I'm I'm extremely grateful to have met him, to have uh, to have worked with him, to somehow somehow learn his point of view and be influenced by his point of view, and that's um, so I was gonna talk. I'm not. There's gonna be no new math in this talk. I'm just gonna talk about some of his favorite, very favorite kind of, um, and maybe that's one of his most, and maybe one of his most favorite pictures. Is that, of course, one finite set that is he liked very much. Of course, the representation. So if I look at the EREPs of the symmetric group, that this is the same as partitions of n. So it's a set of lambdas partitions of n. And there is, of course, a geometric way to draw a partition like so. It's actually I think it's Vershik and Karov introduced this way to drawing a partition. That's, of course, everybody would agree that's much more balanced, and also save space on the page by root 2. Um, so this is somehow that's and one and this set has a natural measure, namely if I assign the measure of each partition to be its dimension squared divided by the order of the group, which is n factorial. So this is a probability measure. It's natural measure that would appear in harmonic analysis on the space, and incidentally, maybe for for the reasons that eventually we're going to come back to that. This is also the product over all squares in these partitions. of 1 over the hook of that square squared. So so this is something like that, right? Or maybe so so this is, maybe I'm missing the overall n factorial, but that's roughly correct. And so then and so what's the hook? Hook is the, if I have any box, then the hook is the length of this whole thing. And so if you take the log of that expression, this would be well approximated by a double integral, with the kernel being log of the, more or less log of the distance between the point. And and you can see, and you can, so you can ask, when this clearly gives you a variational problem, which says what is the representation that packs all the, in the limit when n goes to infinity, what is the representation that packs all this uh, all this Planck measure. In other words, what is the, there will be, if you embed partitions, so if you embed partitions by scaling, so maybe we scale partition by root n, so that would be that this figure will have area 1, and this embeds this sets into Lipschitz 1 functions. Lipschitz 1 functions, the compact set. And so then you have then below a law of large numbers will tell you that there'll be one shape that the law of large numbers will say there's a limit shape, namely the Planck measure in this space concentrate on one particular thing, which which Vershik and Kerov, and so on one hand there was Vershik, the work of Vershik and Kerov, and everybody always says Vershik and Kerov because in Russian alphabet Vershik goes before Kerov. Of course, in the English alphabet you would have to order it differently, but everybody says Vershik and Kerov, and that's somehow correct. Kerov and Logan and Shep. It's not like that. They computed this limit, and it's given by a formula like that. So maybe we will okay, maybe we're not gonna discuss this formula a little in many details, other than the fact that this actual non-trivial limit shape goes from -2 to 2, and then just continues to be just the graph of the absolute value of x. And this has an interpretation that says that there was a question of Coulomb, that if I take the longest increasing subsequence, longest, it's not like it's bad, longest increasing in a random permutation Sn, and I normalize it by root n, then this converges in probability to in fact 2. And so since this is a moment when we remember Vershik, it may be also appropriate to correct. Sometimes people, they just hear certain things and they repeat it without checking the facts or thinking about them. So in this case, the checking. Everybody says that was proven independently by Vershik, Kerov, and Logan Shep. But the computation of the limit shape only gives you inequality. It says that if you compute the limit shape, you have the inequality that at least this much. But in there, Vershik and Kerov also prove the reverse inequality. They really prove that limit is 2. So I mean, that was the Solon problem was a very important problem at the time. And so that's maybe when people cite its solution, they by and large they make this mistake. So this is maybe one thing about this shape is that instead of this formula, it's much better to look at its derivative, and I will just be in general. So its derivative is just that. So this is maybe I'll move this thing here. So instead of computing what is the actual shape, it's much easier to say what's its gradient. And this will be a feature of a general thing that I want to discuss. Now, also another thing that Antonio Mesic really liked is that if instead of the Plancherel measure of precision, you can take a uniform measure of precision. So uniform measure on precisions of n, and this will have its own limit law, which this is also something we actually computed. So, well, it actually was also computed before him, but and this in this case has this particular formula. So that's and this this funny constant here that has to do with the fact that if you make the probability instead of taking uniform measure on partitions of n, if you make the probability of a partition to be proportional to some variable q to the power n, then the expected size of the partition, that's the Eisenstein series. And this is sine 2 of q. It's also kind of q z. It's a q analog. Q analog of zeta of 2. And this zeta of 2, that's what sits here. And but you think that this is maybe just you think maybe this is just two completely unrelated things, the Plancherel measure and the uniform measure, but in fact they're both some slices in a problem that was extremely dear to Vershik's heart, and he was very so. This is a problem about um, the limit shape of a three-dimensional partition. So if I take a uniform, uniform measure on 3D partitions of n. So this is a finite. So you can imagine that if we draw this diagram, let's represent a two-dimensional partition, then the same kind of object you can consider in any dimension, and in particular you can study in three-dimensional picture, and then this was one of Anatoly Moiseyev's favorite things. He was able to prove that there is a limit shape, but he didn't have a formula. Uh, and the way it's related, so when we look at the formula, 1 second, then the way this appears is that this part, so you see there's a, so this is you take a, and this I believe this will also be discussed in Alexei's talk after mine. So, but anyhow, so if you've you have this limit shape of the same thing we had in for Plancherel measure. There were some parts of the limit shapes that were just straight lines, and some part of the limit shapes were actually curved. And the same here. There are the three things which are just flat, so to speak. Flat. If you think of a three-dimensional partition as something has to do with like at the corner of a crystal, that these flat things are the facets of the crystal, and the curved part, that's the rough part of the crystal. And so it's this the uniform partition is just the it's just this. So this is where the uniform partition sits. Uniform 2D, that's just the boundary of that's the boundary of the facet here. And the Plancherel sits if I slice it, so I can instead slice, like perpendicularly, like so. So this principle I can slice it at any point, but if I slice it in the limit of where it scales suitably, if we're going to what happens near the edge, what happens near the edge of the crystal as I look at infinity of that crystal. So at infinity, that would be the Plancherel. That's the Plancherel. That's the Plancherel limit shape. And you can discuss uh, physical reasons why it's so. It's not hard. This can be argued, but much easier to see since there's good, extremely good formulas for what this limit shape is. It's much easier to argue with formulas. Uh, and the first formula for this object was published by Kenyon and Cerf. And in modern language, what this is that this says, so it's kind of in modern language, it says that this limit shape this is the Ronkin function of a straight line. So I think I'm not sure. I think Vershik knew Ronkin. I think he was when this when this description became available. I think he was very happy, but I'm not 100% sure. So I think that they so so what is a Ronkin function? So Ronkin was interested in um, if you've ever studied things like Jensen inequality and whatever Hadamard three circle type of theorems, somehow distribution of values of entire function, then you see the average of the log of the absolute value of an entire function taken over circles of different size. And Ronkin was interested in similar questions in for holomorphic functions of several complex variables. But in particular, among holomorphic functions of several complex variables, you can also take a so this is not what Ronkin wanted to study, but you can plug in. So this is instead of entire function of that, you take a polynomial. So Ronkin would say take an entire function. We can take a polynomial, and then we take the logarithm of absolute value of a polynomial, and then we would like to take compute its average over the set where the absolute value of z is fixed to be exponential of some number x, and absolute value of w is fixed to be absolute exponential of some number y, so it's a big function of y, so this is called the Ronkin function. And somehow the crucial fact about this sort of things is that they're convex, and that's also true here. And what would that function look like? So, well, let's see, where would that function in principle have singularities? Well, in principle, it has singularities. So if this is now a polynomial, that would have a singularities where it will have a singularity. So that would be where the integral will have singularity. The function itself is, even once differentiable, but the integral, might have singularity. So if I look at the locus pzw equals 0, that's some algebraic curves inside. So this is sits inside. Well, let's say, what do you take non-zero things? So I take c star squared and some something like that. Of course, it's not since I since I forgive since I disallow points that where one of the coordinates is either 0 and infinity, maybe I should puncture some of these points out, where one of the coordinates is 0 and infinity. And then if I take the map, which takes the log of absolute value of z and log of absolute value w, then the points I punched out, they would be the points that at infinity of this. So these are the points I punched out. And the rest would look like this figure that is that Gilfan, Kapranov, and Zelivinsky called amoeba of P. And then the Ronkin function, it will have the Ronkin function would be linear on the complement of the amoebas. That will be linear. And in the amoeba will be linear with the slope with some specific slope. In fact, it's like the Jensen inequality with specific slope. And then and then over the amoeba that will be a smooth sort of kind of smooth convex interpolation. So that will look like the minus the Ronkin function. Here will look something like that. Minus the Ronkin function would look something like that. But so, but in particular, if we take and I believe this things like this will appear also in Alexei stock. And but if you're for a straight line, so now if P of ZW, if P ZW equals is just Z plus W and then plus one or minus, it doesn't really matter. So then this amoeba just will have no holes and will look just like that. And there's only three, you remove only 3 points. There are three, they intersect the coordinate axis at 3 points, so you remove 3 points at infinity here. And this figure will look exactly like that. So that's the picture. That's the Ronkin function of straight line of z plus w equals 1. And moreover, you can if you have that the actual if you think about how this actually computed, it actually computes something stronger. It says that the not just the not just the limit shape is this, it's also says about so in all of this problems, there's always when you have a some sort of random surface with interaction or probability measures defined locally, there is a function called surface tension called which describes to you what is the how much the surface likes or dislikes to have a given slope. And by like and dislike, I mean how many surfaces, if what's approximately the logarithm of the number of surfaces that have that slope. So if you study something random in d spatial dimensions defined by local interactions, then you'd imagine that the logarithm of the logarithm of the kind of things you can have that uh, that is, so to speak, that's somehow additive, being so the interaction of local, it's additive over over your domain, and scales is the dimension of the domain. And so there's this there's this function called the surface tension, and what the surface tension is, which you maximize or minimize to get the limit shape. So it just says this sigma, maybe call it surface tension, is in fact is the Legendre dual of the Ronkin. And this continues to be, this can be deformed many different directions. Like for instance, I think Alexei will talk about periodically weighted things, and if you have a periodically weighted things, then you're the same. So if you have a three-dimensional partition or a similar object and it's weighted periodically, then everything will stay the same except your curve. Instead of being a straight line, this will be some actual genus G curve, and so then you'll have in the periodic situation, you will have a non you will have, so if you have a periodic weighting, you will have this non-trivial facets open, and the corresponding surface tension have singularities at this point. Because Legendre, if you have a flat thing in a function, then in the Legendre transform you will have a singularity. That's so. This is past this description. And from this, you can in fact, from this description, you can in fact solve. So first of all, what is the variational problem? So you want to say, what is the variational problem? The variational problem is that if h is the height of the limit shape, in order to describe your limit shape as a function, just like when we had this Vershak-Kerov shape, we took a partition, described it the set of a Lipschitz function. The same thing you can do here. You have the graph of a Lipschitz function. Then what you need to maximize or minimize is this function sigma of h t area. You want it to be, well, let's say depends on the size. Let's say maximize, and then with the constraint that the whole h is fixed. Is there a question? No. Right. So this is, this is roughly log of probability. So you would like it to be maximal with the constraint of your partition of a given size. Then it was, is that okay? And also, I'm not, so I started at some kind of random hour, and I'm not really keeping track of time, and I can stop at any time. So when it's just time to stop, just tell me stop, because I don't want to run over time, and it's just, there's no, yeah, I can speak about the subject for a long time, but it's, we're here to just basically pay tribute to Vershak's vision, and that's, I think, yes.
You have 15 minutes.
I have 15 minutes left?
Yes.
Oh, great, thank you, that's good. And why is this, interesting is that, and also, of course, you have a boundary condition, so plus the boundary conditions. All right. So this is what so h is now a function of two variables, and so this is, while you have a function, if you in one for two-dimensional partition was h was a function of one variable, and so then, okay, there's a boundary condition in that case, just whatever the value at the endpoints of the interval. So that's, or at least for a two-dimensional partition, is the boundary condition that you're asymptotic to, or you coincide with the graph of absolute value of x at infinity. And of course, when you look at function of two variables, then your boundary condition is a function, an arbitrary function, and so that says that there's a much more variety, much more flexibility in setting up this variational problem, and but coming out of this description as a Ronkin function, there is a kind of uniform way to solve all these problems. Like, maybe many of you, and maybe seen this picture before, that if my boundary conditions are such that this three-dimensional partition had to fit a box without a corner, something like that, then a cardioid limit shape will 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 uh, will develop. And well, I think this is actual cardioid. This shape is actual cardioid.
Excuse me, Ronkin function is the Wolf function in this, yes?
What?
Wolf function is the same as Ronkin function.
Um, yeah, you can say that. Yeah, but more important is the surface tension. What's Wolff theorem just says that if you have the Legendre dual of the surface tension, always solution is always a solution to the to that's basically Wolff's theorem, right? So so um so this is without the volume constraint. So if you're in a finite box, you can ask you can you can fix the volume under the graph or not fix the volume under the graph. Under this will be just some Lagrange multiplier in your variational problem, which is you can set to 0 if you want. And with the volume constraint, this is a cardioid. A cardioid in exponential coordinates. And the exponential, so when you exponentiate the coordinates, there's a constant. That constant is the Lagrange multiplier from the volume constraint. And the way you construct the limit shape in this and in general is that you look at the following picture. In principle, this is a point inside the limit shape, and then and you mm, which is, like I said, I mean, in general, some exponential coordinates, but let's say, I mean, just this exponential coordinate, just know it, just really x. And then you can ask for what about the tangents through a point to my frozen boundary in look at tangents. And the reason that we have the tangent is important, but the fact that it's a tangent line, the fact there's a line here, line is because the is because my function PSW was z plus w minus 1. So this is why it's a line. Otherwise, some other algebraic curve. But anyhow, it had to be tangent to my limit shape. And what bounds the limit shape is called the frozen boundary. And the basic geometric fact is that this will have some number of tangents outside. So if you look at the cardioid, outside of the cardioid, it will have 3 tangents. And inside of the cardioids, two tangent things will go complex. So instead of the and more generally, so you'll have some number of tangents outside, and 2 of them will go complex inside. And so then inside the so people say this limit shape has some boundary, which is boundary between order and disorder. So that's a boundary of the facets called the frozen boundary. And what's inside the disordered region, or the rough region, is sometimes also called the liquid region. So all these words are used interchangeably. And so then you have inside, you have this special function, which is for every point inside the boundary, there is one and only complex tangent to the cardioid, and this up to conjugation. And this complex tangent line, you can you have three things. So what do you mean point to line a line? It means 3 things have to add to 0. So you have a triangle in the complex plane, and a triangle in the complex plane determines you 3 angles. And if you take a complex conjugate, the same 3 angles. So these are defined unambiguously. And these three angles, that's the direction of the normal to the limit shape. So that's a general, that's like that's a generalization of the formula. So if you go back to to what we had at the beginning, what was that? This formula. So the derivative is given by something like that. That is really the generalization. This formula here. You go back 100%. Yeah, that makes sense. So now to conclude, and how much time do I have left? I have
I think 5 minutes or
5 minutes. Okay, 5 minutes. So to conclude, maybe I want to say why. Well, at least one explanation. Why was that the case that uh, that Anatoly Moisеевич was, with this petition and stuff, started things which were, led to so much beautiful mathematics. Why is there all this? Why is that the case? Is that the I apologize. Yeah, it's because he also studied limit shapes and many other problems, and maybe eventually they will also lead to a similar amount of beautiful mathematics created, and so it remains to be seen. But with partitions, what I consider to be the fundamental reason, and and the fundamental reason is that partitions, two-dimensional partitions, three-dimensional partitions, so on and so forth, they have to do with really fundamental objects in algebra, in geometry, and they have to do with monomial ideals. So if you have an ideal in the ring of polynomials, say two variables, of course there's some interesting ones. They're parameterized by interesting algebraic variety called the Hilbert scheme. But if you look for those generated by monomials, which is equivalently to say the that they fixed under rescaling of the, so if you rescale both variables, your ideal is fixed. Then very plainly, this is, if you have generators, let's say this for monomials, that what is in the monomial is a shape like this, and what's not in the monomial is essentially a two-dimensional partition, maybe with infinite legs. And the same thing is true in any number of variables. So if you want to in three dimensions, like if you study if you invert, so we looked at this corner of the crystal where you have a limit shape of three-dimensional partition. If you invert, if you instead of boxes that are there, plot the missing boxes, that looks like that, and that's a three-dimensional partition. And then, moreover, you can instead of taking of ideals in local coordinates, you can talk about like shifts of ideal that make coordinate changes. And that means you'll be doing things like you'll be doing gluing these pictures, something like that. This represents something which looks like this ideal in one coordinate and something that looks like that ideal in some other coordinates. And so this connects, and the reason this is the particular measures you get have to do with the fact that, remember that the basic ingredient of like Plancherel measure, that had to do with the hook. But hooks are there are special cases so if a box that has a notion of arm, well, it has a notion of leg, has a notion maybe plus number plus. So this number is called the arm leg and leg length of a partition, and that have to do with these objects have to do these things have to do with the tangent spaces. to these monomial ideals. And the at the corresponding or deformation have to do with deformation these monomial ideals inside of all ideals. And so that this sums this version, the Planck real measure, that's a basic thing you would sum in things which are now called Nekrasov theory or Nonson-Thomas theory, like this original curve was started. Like this thing was started. This would be so this two-dimensional partition. This is something you would be summing in, so to speak, Nekrasov theory. So that would be saying that this limit shape is this Albrecht-Whitman curve for kind of pure U1 theory. Instant on. And then there's a generalization when you somehow replace it by some rank, and then this would have a feature that it will look like just this. So the way it will look like, it will have. So instead of being a cross section here, so we had a cross section. We had a cross section here, and instead of being so simple, it will now, if we look at things here, that will have some mini flat piece in higher rank. It will have rank plus one flat pieces. And then this for this thing, this is the same. This is also Albrecht-Whitman curve for U1 plus a joint map. And in general, these limit shapes, they're mirrors of toric, Calabi-Yau manifolds, and then this is the and there's much beyond that somehow. There's lots of math that takes this limit shape construction and puts it in much richer context. Well, maybe I will conclude my talk, and thank you so much for your attention.